Work and power are words that we use in our everyday lives, but when we use them in the science world, they have some slightly different meanings. Today, we're going to talk about work and power. This is our second day of going over work and power in our classroom. So just a quick look at our agenda. We're going to review from a check for understanding that we just did. And I want to let everybody know that our summative assessment has been moved to October 8 and 9. So you have an extra class day to study and practice. Today we're going to do work and power calculations. You'll have a quick demo. You'll fill out some information in your notebook, and you'll have some worksheets and practice problems to do. We'll have a Kahoot so that we can quickly get everything into our minds so that we're ready for a formative check today also on work and power. So from the most missed questions from our formative last time, we were looking at Newton's laws. So here's a question that a lot of people missed. Just want to go over it. A 1-ton truck and a 2-ton truck are stopped at a traffic light. Assume the trucks will have similar engine power and tires. If the drivers apply the same amount of gas at the same time, how will the acceleration compare between the two vehicles? Here are our option choices. The 1-ton truck will move forward first. The 2-ton truck will move forward first. Both trucks would move forward at the same time. So when you get a question like this, it's kind of wordy and has a lot of information. You want to ask yourself, what is this really asking? What does it tell us, and how can we use what it told us? So the information we know that we have a 1-ton truck, we have a 2-ton truck. We know that we're going to apply the same amount of gas at the same time, and we want to know what is the acceleration difference between the two. Okay, so we want to know really, in layman's terms, which truck will move forward first. All right, we have two objects. One has more mass than the other. One truck is 1 ton and the other truck is 2 tons. So which of Newton's laws talks about mass and acceleration? Both of those ideas are in this problem. That's Newton's second law. Force equals mass times acceleration. So we're trying to figure out what happens to the acceleration from one truck to the other. Last class, when we went around the room and had different stations, one of the stations had you kind of apply the same force to two different objects. One object has more mass, one object has less mass. In our classroom, we had 2 little cylinders, and one was clear plastic and it was lighter or had less mass, and the other was a metal cylinder of the same size, but it had more mass. When we flicked those two objects or applied the same force to them, the lighter object moved faster and sometimes further. So we're going to think about that. All right, back to my problem. I have 2 objects with different mass. The one with the smaller mass is probably going to move faster based on what we did in class with those 2 cylinders. So the 1-ton truck will move forward first in this problem. Another problem that several people missed was this one. It says, which of the actions below best illustrates Newton's third law of motion, which is our opposite and equal forces law? Here are our options. A bowling ball rolls down a bowling alley. A child's swing keeps on moving after being pushed. A jet engine propels an airplane forward. What is it really asking? It wants to know which of those 3 scenarios is best showing Newton's third law. Newton's third law says for every action there is an equal and opposite reaction. All right, so I'm going to look at the first option. I want to know which one of these shows equal and opposite forces, but the first option says a moving bowling ball has no new forces. It's moving because of inertia, right? A bowling ball rolls down a bowling alley. It's not changing its direction. It's not changing its speed because no new forces are acting upon it. So it's just continuing to move because it has inertia. A child's swing keeps moving after it being pushed. It has no new forces. It was pushed and then maybe somebody walked away. It's still swinging. It has inertia. So inertia, of course, is the first law of motion. Those are both showing examples of the first law of motion. That leaves us with our third one. A jet engine propels or pushes an airplane forward. So what's happening is fuel is burning and pushes a force backward, and the jet moves with an equal force in the opposite direction to the burning fuel, so it's going to go forward. So that's our answer, that third one. All right, last class we talked about pulling an object up a ramp at different heights, and we compared that to just lifting the object straight up at those same different heights. And so we measured force using a spring scale and tried to think about the amount of work that is done. Remember, an inclined plane is just one of our 6 major simple machines. It's designed to help us decrease the amount of force needed to make something happen. So in your notebooks last class, you had recorded the distances that we used with our inclined plane and also just straight vertical movement. And you recorded the amount of force that was required in those scenarios using the spring scale. This is information we gave in class. And then for homework, you were calculating work in joules. Remember, to calculate work in joules, we just have to multiply force times distance. So just quickly look at your notebook right here, page 22, and check and see if you have all of the correct amounts of work. Work is in joules, just another reminder. Okay, so check your work right now. And remember, you can always come back and look at these slides in Schoology. So in your notebook at the bottom of page 22, you'll have some space. This question is not written down, but I'd like for you to think about the answer to this question. How is the force that's required to lift an object straight up different from the force required to pull that same object up a ramp? Talk with your table mates and then see if you can come up with an answer and write it down in your notebook. In class, I'll give us some time for this. On the video, you can pause if you need some time. So, hopefully, as you talked with table mates or thought about this yourself, you realize that less force is required to pull an object up a ramp. And of course, the steeper the ramp, the more force you need, but still using a ramp is going to require less force than pulling an object straight up. Simple machines do help us work more efficiently. And a ramp or an inclined plane is a simple machine. In class today, we're going to talk about power, which is just how quickly you can do work. So we have a dowel, that's like a stick, mass system, and we have a mass hanging from a string. That string is attached to the dowel. We're going to roll up the dowel and pull the mass up for 1 full meter. Our string is 1 meter long. We're going to roll that dowel up until we pull the mass exactly 1 meter. And so we can calculate the amount of work we're doing because work is force times distance. Also, we can time ourselves and we can figure out exactly how much power is required to pull that mass up. In class, we'll have a quick demo of this. So, I'd like for you to record this data. This is on page 23. You've already glued this in your notebook last class. You're going to record the data that we're giving you right here. We had some superheroes come in and roll that dowel and pull the mass of 500 grams up. So Superman used 49 newtons of force because that is the force that is applied to a 500 gram mass that's just hanging. When we hang that mass from a spring scale, remember, force is mass times acceleration. The mass was 500 grams, and we have a universal acceptance that acceleration due to gravity is 9.8 meters per second squared. So it's the same force for every single superhero. The same force is being applied to that mass. Also, every single time they roll it up the dowel, they are rolling it up that dowel exactly 1 meter. So everybody has the same force and the same distance. So we're going to calculate the amount of work that's done. Remember, over here you can see work is force times distance. So we're just going to multiply these two numbers together. 49 times 1, of course, easy. We don't even need a calculator. It's 49. Okay, and then we're going to want to calculate how much power was used. So in order to do power, we have to say the amount of work in joules divided by time in seconds. Okay, so we recorded how long it took Superman to roll up that mass to the top of the dowel. It took him 21 seconds. Green Lantern got it done in 15 seconds. And you can see the Incredible Hulk. He took 18 seconds. Black Widow took 19 seconds, and then Aquaman took 18 seconds again. So we have already calculated work because it's just 49 times 1. And now we're going to say power is work divided by time. So we're going to divide 49 joules divided by 21 seconds to figure out the work that Superman did. Work is going to be in the unit of watts. Okay, so please calculate work and power for each of these instances. And then at the bottom of page 23, write which superhero used the most power, or was the most powerful in this case, and what do you think caused them to use more power? Or more importantly, how do you know? How can you tell that they used more power? In class, we'll give you some time to do these calculations. If you're watching the video, you can pause and do the calculations and then restart the video. All right, so thank you so much for doing that. You, of course, were allowed to use a calculator. Right now, we're going to have you check your work. So you've already done these calculations. Just check and see. You hopefully have 49 joules for each case because it's always a 500-gram mass that is being acted upon by gravity, which is 9.8 meters per second squared. So our force is always 49, and the distance is 1 meter. Okay, everybody did 49 joules of work. Now, the thing that's different is our total power. Power is work divided by time. So again, Superman, 49 joules of work divided by 21 seconds is going to be 2.3 watts. Green Lantern, 49 joules of work divided by 15 seconds is 3.3 watts. For the Hulk, 49 joules of work divided by 18 seconds is going to be 2.7 watts. Black Widow did 49 joules of work in 19 seconds. Black Widow has 2.6 watts. And Aquaman, 49 joules of work in 18 seconds again, so he's same as Hulk. So he got 2.7 watts. We can see the amount of power used. Which one was the most? That's 3.3. That's our biggest number here. And who was that? Let's look over here. Green Lantern. Green Lantern is our winner. So Green Lantern used the most power. He was the most powerful. And why? What was the difference? Well, he did it the fastest. Okay, that's how we figure out our value for power. We divide work by time. And since his was the smallest amount of time, he was the most powerful. He had the highest number of watts, most power, and it's because he turned that dowel fastest. All right, we're going to do a little bit of extra practice on net forces. So remember, force is just a push or a pull. And so if I look at net forces on this little red car, I have 125 newtons pulling to the left, and I also have 375 newtons pulling to the right. I want to know what's the overall net force, how many newtons, and then also what's the direction of movement. So we hadn't really practiced this before, but if I'm pulling left for 125 newtons, I'm pulling right for 375 newtons. Whichever one is higher, the direction that the higher amount is going, in this case, that's the direction my whole car will move. And I can figure the net force, because it's the difference between the force that's pulling left and the force that's pulling right. So in this case, net force is the difference between the opposite forces acting on the object. They are opposite forces, right? All right, so for this example, 375 newtons minus 125 newtons equals 250 newtons. That's our net force. That's the overall, after everything's said and done, difference in force. 250 newtons is the net force, and the car will move to the right because that bigger force is pulling to the right. I know it seems pretty simple, but when you get ready to be quizzed and tested on this material, you'll want to be able to see an image and kind of figure that out. Okay. Next, we have more net force practice. In this case, a beach ball. We have 12 newtons of force pulling this ball up, 8 newtons of force pulling this ball down. So again, we want to know net force and direction of movement. Net force is the difference between the opposite forces acting on the object. These are opposite forces, right? So one is pulling up at 12 newtons, one is pulling down at 8 newtons, and I'm going to find the difference. 12 newtons minus 8 newtons, because those guys are pulling against each other, they're canceling each other out. That's going to leave me with 4 newtons. 4 newtons is my net force. Which direction is it going? Are we going up or are we going down? Look for the higher amount. We're going to go wherever that higher number was in the first place, and so the bigger force is pulling up. That ball will move up. A third practice problem. This time we have forces showing that we are moving up and down, or we are at least, applying forces up and down. Can't say whether we're moving yet. And if you notice, this time I have one guy pushing this chair to the right and another guy pulling this chair to the right. These are not opposite forces. They're in the same direction. So since they're in the same direction, we're actually going to add them together. So looking at this chair, remember a net force, that phrase, is the difference between the opposite forces acting on that object. So if I look at my up and down forces, those are opposite forces, right? So I'm going to find the difference between those forces, okay? 85 newtons minus 85 newtons. It turns out vertically, so up and down, we don't have any newtons. 0 newtons net force. That's the overall force up and down. So 0 newtons is the net force up and down. That means it's not going to be going up or down. Side to side, what do we notice though? This time, look, our forces are going in the same direction. They are not opposite forces. They're the same forces. They're not opposite. So we're going to add these forces together. They're both going in the same direction. So 65 newtons, this guy's pushing the chair to the right, 65 newtons. This guy's pulling the chair to the right at 70 newtons. So our total newtons, our net force, the overall force side to side, is 135 newtons. 135 newtons is that net force going to the right. So which direction will the chair move? The forces up and down are equal, so it will not move up and down, but the horizontal forces are both pushing it to the right. All right, so we need to understand net forces, but then we're going to go a step further. Once we understand a lot about our forces, we can determine how much work is done by multiplying force times distance. And we're going to use this handy triangle again because that's an easy way to keep track of our formula. Work equals force times distance. So if I'm looking for work, I would cover up the W and I have force times distance side by side. A rock climber wears an 80 Newton backpack while scaling a cliff. After 30 minutes, the climber is 20 meters above the ground. How much work is done on the backpack? So here's our question. Always make sure you know what's being asked. How much work is being done on the backpack? Well, work is force times distance. So I need force and I need distance, right? So let's go back to the problem. Can we find force? A rock climber wears an 80 Newton backpack while scaling a cliff. Well, there's our force right there. 80 newtons of weight that backpack has. And I need distance, force times distance. So I keep reading. After 30 minutes, minutes is not distance, right? That's time. So I'm going to keep going. After 30 minutes, the climber is 20 meters above the ground. There's my distance, 20 meters. So I have force is 80 newtons and distance is 20 meters. Let's do the math. Force is 80 newtons distance is 20 meters, and work is just force times distance. We'll plug in what we can. Work is 80 newtons times 20 meters. It's 1,600 joules, or 1,600 joules, either way. I have the same example. I still have that rock climber. He's wearing an 80 Newton backpack while scaling a cliff. And after 30 minutes, the climber is 20 meters above the ground. This time I want to know, what is the climber's average power? So I have a different triangle. We will typically offer you formulas. Power equals work divided by time. Power is just how fast can you do that work, right? So I'm going to need work, and I'm going to need time. When I look at the problem, it doesn't specifically give me the amount of work that's done. But remember, we just calculated that on the last slide. I'm backing up. We just calculated work is 1,600 joules, right? We can find that information. Sometimes it just takes a couple of steps. So again, I'm going to do it one more time. We're going to do work is force times distance. And once we figure out work, then we're going to divide by time. If you'll remember, though, we always have to have our time in seconds when we are calculating power. So in order to convert our 30-minute time, we're going to multiply it by 60 seconds over 1 minute. Why? It's because 60 seconds is 1 minute, right? So if I make a fraction where I have the same thing divided by itself, that is equal to 1, right? If I said 5 over 5, that equals 1. So 60 seconds and 1 minute, they're equal. So I'm not changing my numbers, I'm just changing my units. If I multiply 30 minutes times 60 seconds per minute, watch what happens. Now I multiply my numerator straight across, and I multiply my denominator straight across. There's no denominator here, it's just 1. And my units for minute cancel. I'm just left with seconds. Fancy, right? So I end up with 1,800 seconds. All of that is just telling us that 30 minutes is the same thing as 18 seconds. All right, what are we doing again? We're trying to find average power, and power is work divided by time. So a quick reminder, our work that we figured out, work was force times distance, or 1,600 joules. Okay, so I know power is going to be 1,600 joules divided by 1,800 seconds. 1,600 joules divided by 1,800 seconds leaves me with 0.89 watts. And I have figured out the power required for that rock climber to climb for 30 minutes up 20 meters with a backpack that has a weight or force of 80 newtons. You can come back to this video at any time if you want to try to get a reminder about converting minutes to seconds, or just refresh your memory about how to find power. Power equals work divided by time. All right, so you have some work and practice problems that you can be doing. This is a separate worksheet. That's actually going to be your your separate worksheet. In your notebooks already, you should have page 24. I want you to do page 24 first. Do page 24 first, and if you finish all of the problems on that page, then I want you to start working on the additional practice problems. The more practice, the better, so that you can feel really comfortable doing these math problems in your science class. Of course, you can use a calculator. Make sure every time you're looking at the problems, you're reading through carefully. You want to figure out, what are you trying to answer? And it's helpful to even underline. So when I read this one, Maya can perform 2,000 joules of work in 15 seconds. What is Maya's power output? I might underline the word power and remind myself that I'm going to say power equals work divided by time. Then I know what to look for and what to plug into those formulas. All right, so in class, you'll be working on these problems for a little bit. If you are watching this video not in class, you can pause the video as you're working on these problems. And then we're going to spend about 8 minutes on a Kahoot. I'll add that Kahoot link after we've had our class as solo practice so that if you miss class, you can practice. And after our Kahoot, everybody will go into Schoology to do this check for understanding. This is lessons 6 through 10. So we're covering a lot of material on motion, work, and power. And so you'll just read each question carefully, do your very best to answer it, and use a calculator. Remember, if you're struggling with a question, you can pause on that and you can skip it. Move on to some other problems that might even remind you of formulas or information you need, and you can go back to your skipped questions at the end. Okay, when you finish your quiz in class, you'll go back to your practice problems that are in your notebook or on separate worksheets, and just make sure that you are getting lots and lots of practice on work and power.